So these are the contents of this lecture. Firstly, we will discuss what is the classical field theory electron and what are the postulates, demerits and the merits, and the quantum theory. So we will discuss these merits and demerits of these two theories. So in this chapter, we will discuss free electron gas model, and this free electron gas model can be explained by the classical theory of free electrons, and many properties, physical or electrical properties of the metals can be explained using the classical theory of free electrons like thermal conductivity, electrical conductivity, specific heat, magnetic susceptibility. So these are some properties that can be easily explained by the classical theory of free electron. And but there are some concepts and the phenomena and some parameters that are not explained by the classical field electron theory, and these can be explained only in the quantum field theory. And what the difficulties and the demerits that occurred in classical theory, we will discuss in the quantum field theory, and those difficulties are totally removed in quantum field theory. So now what is classical theory of free electron? And this classical theory of free electron was firstly proposed by P. Drude, that is Paul Drude, in 1900. So in 1900, Drude proposed this theory, and according to him, metal crystal consists of positive ion cores with their valence electron. You can see here this figure. You can see here this figure showing the metal crystal. Can you see this? The arrow I am drawing on this. So this is a metal crystal, and you can see here there are the positive ion cores and the valence electrons are seen here. So in 1900, Paul has suggested this, that metal ion consists of positive ions and the valence electrons, and these valence electrons in the metal are free electrons, and they are free to move inside the metal, and the electricity that is conducted by the metals is only due to the presence of these valence electron, and that's why these valence electron are also named as conduction electron. So this is suggested by Paul Drude in the 1900, and these free electrons, the valence electrons, they obey the laws of classical mechanics. You know what are the laws of classical mechanics, what are the Newton laws. So these free electrons in the metals, they obey all the laws of classical mechanics due to this classical theory of free electron. And in 1909, then Lorentz suggested that if there are these electrons are free inside the metal, so these electrons can be treated as electron gas, just like a perfect gas in a container. If suppose you have a container and a perfect gas in it, so how it behaves? So there is its behavior is just due to the gaseous state. So the electrons, if they are in the metals, they are just behaving like that. It's like a electron gas. It is suggested by the Lorentz in 1909. So, and this free electron gas that obeys the Maxwell-Boltzmann statistics as just like the perfect gas. So, and this electron theory can be applicable to all type of the materials, metals and non-metals, because firstly it was introduced by Drude, and it is applicable to metals, but when it is again refined by the Lorentz, suggested that electrons we can treat as electron gas, so this can be applicable then to metals and non-metals as well, and it can explain all the these parameters and properties, electrical and thermal magnetic properties of the solids. These can be easily explained by this classical theory of free electron, as it is suggested by two persons, Drude and Lorentz. That's why classical theory of free electron is also named as Drude-Lorentz theory of free electron. So is it clear what is this classical theory? Because firstly it was proposed by Drude, and according to him, This is the metal structure, and metal structure have positive ions and the electrons. Then Lorentz suggested this is the electron, these are the electrons that are moving inside the metals. We can treat these electrons as a electron gas, just like a perfect gas. Okay, so and they also obey the classical laws of mechanics, and they obey Maxwell-Boltzmann statistics. So this is a theory of free electron, that is a classical field, theory of free electron by Drude and Lorentz. So now postulates. What are the postulates of this classical theory of free electron? You can see here, these are the figures. These are the figures of metal crystal. This is metal crystal, one of the picture, and this is second picture that I have inserted in this slide. You can see that these are the metal crystal that can be seen from the outside. You can see this is a structure of metal crystal, and what is inside this metal crystal? It was suggested by Drude that it consists of positive ions and the negative ions, that is the electron. These are the valence electrons, and they are free to move inside the this metal structure. So if these are free to move inside the metal structure, so why they can't leave this metal surface? So can anyone tell me if this metal surface, because we have not covered this metal, if we have a crystal structure like this, so if the metal crystal is this and we are saying that electrons are free, so why they can't leave the surface? Because you know, in case of perfect gas, if you have a perfect gas, if you have a if that put in a container, suppose you are using perfume, and if you are using perfume at one corner, you know that the fragrance of that perfume, and that goes to the second corner and the other corners to the room very easily, and very fastly it will go. So that means those gas molecules can move very fastly in the room, and if they are free to move. But now we are saying that, yes, now we are saying that electrons are free inside the matter, so why they can't leave the surface? Why they can't leave the surface? Okay, you are saying they don't have enough kinetic energy, and no diffusion in metals, very high electrostatic force of attraction. Yes, it is due to the that electrostatic force, or that Coulomb force, that binds those electrons inside the matter. Because these are free electrons, but these are bound to these positive ion cores due to Coulomb force of attraction. Due to this Coulomb force of attraction between positive ions and the negatively charged ion, do not allow free electrons to leave the metal surface. So is it clear? So why they can't move, or why they can't leave that metal surface? Otherwise, you know, when you are spraying a perfume, so it can go anywhere. But if Lorentz suggested that these electrons in the metals are like electron gas, so they can move, and they should leave the surface, but they can't leave the surface because due to the Coulomb force of attraction between positive ions and the negatively charged ions. And you can see here, this is the perfect gas. If suppose it is a perfect gas, and it is placed in a container, so how it is behaving inside this container? This is a perfect gas, and these electrons behave just similarly like that in a metal crystal. If we have a metal crystal, electrons are like electron gas, and but in this case we know that the field due to this positive ion cores is supposed to be uniform. And what this field is, because we are saying that if you have unlike charges, positive and negative charges, they are attracting each other, and due to some field, so that field is Coulomb field. Now if that field due to this positive ion cores is uniform. Okay, if your field that is given by the positive ion cores is uniform, so the potential energy of that electrons will be taken as constant, because if the field is constant, if the field is uniform, so the potential energy will be fixed, and potential energy will be constant. And in this classical field theory, it is taken as zero for the convenience, because we know that electron energy of any particle is equal to the sum of two energies, potential energy and kinetic energy. But here we are saying that potential energy is constant because the field the electrons are experiencing, it is uniform. So if field is uniform, so the potential energy is fixed. So in this case we are saying we are taking this potential energy 0 for convenience. So the energy of electrons we take it as only equal to the kinetic energy of electrons. So are you getting my point about the postulates? What the postulates we have in this classical theory of free electron? Yes, let me know about this. Only Aditya knows. Shakir. So these are some postulates, okay. So these are some postulates we are discussing for the classical theory of free electron. In this theory, it is in this theory, according to this, there are large number of free electrons in the metals, but they are not leaving their surface due to Coulomb force of attraction, and the field the electron experiencing it is uniform, so the potential energy is constant, and energy of electron we are taking only due to the kinetic energy of electrons, because we are considering that potential energy taken as 0 for the convenience. And the free electrons in this situation, in the metal situation, we are taking it as a gaseous molecule in a container. So the theory of gaseous molecule is also extended to free electrons. Means as Lorentz suggested that electrons in the metals can be treated as electron gas. So the theory of gaseous molecule can be extended to these free electrons. So if the theory of gaseous molecule is extended to these free electrons, so we know that due to the theory of gaseous molecule, energy of electron at a given temperature, we take it as E equal to 3 by 2 kT. Okay, because you can see from this figure, you can see this is the figure of metal structure here, and we can't see these electron gas. Okay, we can't see this electron gas, but Lorentz suggested if there are a number of electrons, number of free electrons are there, so and we can treat these electrons as a free electrons gas, and if this is a free electron gas, so we can apply the theory of gaseous molecule also. According to that, we have taken E energy of electrons that is equal to 3 by 2 kT, and the electrical conductivity in a metal, it's just a consequence of drift velocity in the presence of applied electric field. We know that metals are good conductors. So if metals are good conductor, so why and how they have good conductivity, electrical conductivity, thermal conductivity, so how they are behaving like that? Because in your experiment you have done all the experiment, Hall effect experiment you have done, four probe experiment you have done. So in those experiments you are having some samples. Okay, you have germanium, and in that case you have used simple semiconductor you are using. But we are talking about if this is a metal, so how it behaves. We know that when you are increasing temperature, resistivity of metal is increasing. So how it increasing? Because experimentally we are finding that with the increase in temperature, resistivity increases for the metals. And what about semiconductors? When we are increasing temperature, resistivity decreases. So you have done the experiment for probe, so you have seen there that with the increase in temperature, resistivity decreases. So this is experimentally we are finding how these materials are behaving. But what the theory behind it is, how they do this, why these metals have high conductivity or high resistivity with the increase in temperature. So why these metals or semiconductors have behavior? So some theories behind this. So this is a classical field theory that explains these phenomena, why electrical conductivity of metal is high, and why their variation with temperature is this. Yes, due to the free electrons. And this electrical conductivity we are saying it is due to the consequence of drift velocity in the presence of applied electric field. So these are some postulates. So is it clear? What are the postulates of classical theory of free electron? Because we are saying they have proposed ideas in the 1900, they have proposed these ideas, and now we are studying in 2021 that what are the postulates of those classical theory, because now the physics is somewhat else they have told in the 1900, because this theory they had at that time they don't know about what metal structure they have, how they are behaving like this. So when they started seeing about this how they are behaving, so they have made some assumptions, made some postulates. Okay, there are so many electrons are there, they are behaving like electron gas. So they had, so using these postulates now you can explain everything, why electrical conductivity is this, why thermal conductivity is behavior of thermal conductivity, resistivity. So these are some postulates at that time about the classical field theory of free electrons. So now we will discuss drift velocity. So what is drift velocity? Can anyone tell me? Yes, what is drift velocity, students? Okay, no one tell me. Velocity of electron electric field. Yes. So we are discussing here drift velocity of electrons in the metals or in the conductors. So how it is different from the normal velocity when we are talking about. Because if suppose you have only one electron, if suppose we have only one electron, if suppose we have one electron here and we are giving electric field to it. So how it will move? So it will move according to electric field. So if it will move according to electric field when we are applying electric field to this electron, because it is alone in the space here. So when we are talking about the electrons, when they are present in the conductors, so how it is different from that? Because when it is single electron, so when we are applying electric field to this single electron, so it will move according to that. But when this electron is placed in this conductor, when the electron is in this conductor, so that behavior is totally different, because when it is alone and when it is in the conductor. So this is why the difference in the velocity comes, because when we are applying electric field to the conductor, electrons in the holes are drifted according to that, and they are accelerated according to that electric field. And but at the same time they collide with the lattice vibrations and also with the defects and impurities, because there are some hindrance that is offered to this electron, because if it is alone there is no hindrance in the path, they can move as such. And if it is present in the conductor, so electric field is there, so according to electric field it should have velocity. And if we are saying that there are so many things, lattice vibrations are there, defects are there, so there may collisions that occurs. So if there is collisions that occurs, that leads to some energy loss. And if there is some energy loss, obviously your velocity will get changed, because when electron is alone, velocity it will get. And when it is present in the electric field in the presence and it is present in the conductor, so your velocity will get changed due to collisions. So this is that means that is the interplay between the acceleration and collision process, because we are applying electric field. So if you are applying electric field, acceleration will be there. And but there are also collision process that occurs. So that collision process and the acceleration interplay between them, that determines the steady state drift velocity. So this is difference between the normal velocity when you are giving any electric field to a single electron or a single charge. So it will behave differently when it is present in the conductor or when it is present in any material. If maybe it is in the semiconductor, or it may be in the insulator. So depending that material, how much hindrance is offered to that particle, so your drift velocity will get changed. Yes, Aditya. Okay. So you were talking, we are discussing here about the drift velocity. So is it clear what is drift velocity? Yes, I'm asking to you all. Okay, Akhilesh. Only Akhilesh understood this. What is drift velocity? Okay, so here we are talking about a classical theory of free electron, that in a metal or in a conductor there are a number of free electrons and they can behave as the electron gas, and just like perfect gas. And now here we are talking about electrical conductivity. So if there are so many number of electrons inside the metal, and how they have electrical conductivity, because we are saying that these electrons are free and the electricity conducted by the metals is due to the presence of these valence electrons. So how they are having electrical conductivity? For that we are saying that electrical conductivity is due to the consequence of drift velocity, because if the electrons that are present in the metals or in the crystals, they have so much different velocity, that is named as drift velocity. Because in that case, because when the when the electrons are free, and it is not like that it is just free, because if you have one electron, so when electric field is there, so it behaves differently. But we are saying these electrons are nearly free, but these are inside the conductors, so there is some collision process also there, and so there is interplay between acceleration and collision process. So that gives you a steady state drift velocity, and that velocity, we named it as drift velocity. So is it clear what is drift velocity? Yes, it depends on the material. It depends on the material. Here we are talking about conductor, and we know that the behavior of semiconductors and conductors is different, because we know that when we are increasing temperature, resistivity increases. So if resistivity increases, so according to the material, you have different behavior. Because when we're talking about conductors, so the resistivity increases, and in case when you have semiconductors, your resistivity decreases, and in case of conductors, resistivity increases with the increase in temperature. So depending upon that, you have the drift velocity. Okay, so this is the collision time. Now we are talking about classical theory of free electron, and we are saying these electrons are free, and but there are collisions takes place in between these metals, and we know that no two electrons, if there is a collision and no two electrons get collide at the same time. If suppose one electron is colliding with the other within 1 second, and maybe the second electron may not collide with the 1 second, it can take less time and it can take more time. So these times are different for all the electrons, and if the times between the successive collision is different for all different electrons, so we are taking average time. So that time is a collision time, and it is defined as average time taken by free electron between two successive collisions. So is it clear what is collision time and why we are talking average time? Because all the time, all the collision taking place between the electrons is having a different time, and so we are taking average time, and it is a collision time. So here we are discussing what is the current density. So you know what is current density? That is current per unit area. So here you can see that we have a conductor. Yes, it is current per unit area. And you can see here, this is a conductor. It is in a cylinder shape, you can see here. And this is the area of cross section A, which is, you can see here. And electrons, you can see here, electrons are moving under the effect of electric field. Okay, when we have applied electric field to this conductor, these electrons will move with the drift velocity. Okay, so when they are moving with the drift velocity, and how much current it is passing through this per unit area, so that give you the current density. So if you have a area A and current I, so you have current density, that is I by A. So is it clear about drift velocity, collision time and current density? Yes, I am asking to you all, is it clear? So this is a current density. Okay. So now we are doing the derivation of drift velocity. So in this we are considering we have a conductor and we are applying electric field to it. So if we apply electric field to any conductor, what will happen? Those electrons inside the conductors, they are accelerated. So if they are accelerated, that means there is a why they are accelerated, because we are applying electric force to them. So if you apply electric force, so those electrons are accelerated due to the presence of this electric field. And we also know that uh, in conductors there is a collision process also takes place, because in metals have electrons, even they have the positive ion cores as well. So when electrons are moving inside the conductor, they collide with the positive ions, and even with the lattice vibrations are there. So there is collision process between them, and the interplay between this acceleration and the collision process make those electrons to move with the constant velocity. So what the constant velocity here is the drift velocity. So if we are taking this drift velocity to by given by the expression Vd, so if you have mass of electron as m, so how if suppose if you have force, we have F equal to small e and capital E. So what is this force? This force is a electrical force due to electric field. And if we are saying that this electric field give the acceleration to electrons, so in terms of acceleration we have the formula of electric force, that is equal to ma. So do you know this formula? Yes, students. Yes. Okay, so in this we are considering we have a conductor and we are applying electric field. So if we are applying electric field, so there is electric force. So in using this formula, can you see this formula what I have written on it? So F equal to small e into capital E, and this is the electric force, and in terms of acceleration we know that F equal to ma. So using this relation you can find out the acceleration of electron, acceleration of the electron in terms of the electric field. So this is given by this expression you can see here. This is the expression given by equation number 1. A is equal to small e capital E by m, if m is a mass of electron. So this much acceleration is experienced by electron under the electric field. And we want to find out the formula for velocity, so we are integrating this equation. So when you integrate this equation, because you know that acceleration is a double derivative of this x with respect to time, so when you are integrating with respect to time, so you will get this equation that has a constant c here. And when we apply conditions like when at t equal to 0, this velocity is equal to 0, so c you will get equal to 0. So why we have taken this condition that t equal to 0, dx by dt equal to 0? Can you tell me what is t equal to 0 here? That means t equal to 0 when we have not applied any electric field. So when you have not applied electric field, so why the velocity is 0? These are the initial condition. Yes, okay, this is the initial time. So, but why we have taken this velocity 0? That means no electrons are moving inside when you have not applied electric field. Yes, students? Because when you have not applied electric field, so electrons are at rest. No electric force. Yes, there is no electric force. But what about the velocity we are taking? No potential difference, no electron flow. So that means electrons are at rest. Yes, Prince, I am repeating. We are discussing here the initial condition, what I am saying here, that t equal to 0, velocity is equal to 0. But Drude said what Drude said in 1900, that metal consists of the positive ions with the free electrons, and these free electrons are moving. They are free to move inside the metal. So why we are taking velocity zero? Because when you have not applied electric field, the electron can move in any direction. Okay, in any direction they are moving, they have random motion. So in that way we are saying the average of that velocity for the whole metal or for the whole conductor is zero. So is it clear? Because when we have not applied electric field, that doesn't mean no velocity of electron is there. But when we have applied electric field, so in that way they are getting velocity. But before that, that velocity is zero due to the random motion of electron. And that's why we also told about that when we are applying electric field, so there is a interplay between acceleration and collision. Because firstly, when we have not applied electric field, so there is only collision process that makes velocity zero. And but when we are applying electric field, so there is acceleration, so collision is also there, but acceleration we have applied. So in that way, electron starts moving with the constant velocity, and that velocity is the drift velocity. So this is a condition that at t equal to 0, velocity equal to 0, because the electrons are at that time, they are at random motion. So average velocity they give 0. So we have calculated this constant c equal to 0. So when we put this c equal to 0, we get this velocity. This is the velocity at time t. So this is the velocity at time t of the electron in the conductor when you have applied electric field. So we want to find out the drift velocity formula. For that we are calculating the average velocity between two successive collisions. So for that we have to integrate this equation. So when you are integrating with equation using this collision time, and you get this expression for uh, integrating this velocity. And when you are integrating this velocity from 0 to that collision time, you will get the expression for drift velocity by this expression. So this is a simple formula for drift velocity, because we are saying here that when you have not applied electric field, so at that time only collision process were there, and for that we get the average velocity of electrons to be zero. If the average velocity is zero, that's why we are not getting the current. Now, suppose if you have any metal crystal, so when you have not applied when you have not connected this metal to any battery, so it will not give you the current, because average velocity is zero at that time. Because when you are applying electric field, so they are moving with the constant velocity, and they are reaching at the electrodes and giving the current. So here we now talk about the success of classical free electron theory, and it explains or it verifies the Ohm's law, and it explains electrical conductivity of metals. It explains thermal conductivity of metals. Even they drive this Weidmann-Franz law, and this relationship between the electrical and thermal conductivity. So using these assumptions, those have made by Drude and the Lorentz, they have explained so many properties of the solids. Even they have used oversimplified assumptions for the perfect gas model. They have used, even Drude said electrons obey classical mechanics, even that electrons is a quantum particle. So how these assumptions are very oversimplified, but still they have explained so many things. So this is the success of classical free electron theory. And but there are some drawbacks due to the oversimplified assumptions they have made. It couldn't explain why insulators. So these are some problems or drawbacks from the classical field theory, that they don't explain these experimental facts. Okay, so due to some oversimplified assumptions they have made, so the quantum field theory is therefore, because in case of classical mechanics, they Drude said electrons obey classical mechanics, and then Lorentz said they can be treated as electron gas, and they obey Maxwell-Boltzmann statistics. So you know what is Maxwell-Boltzmann statistics? Have you heard about this Maxwell-Boltzmann statistics? Suppose you have a box, and we have placed two balls inside. So according to Maxwell-Boltzmann statistics, uh, if you have two identical particles in the same box, you can distinguish them. Means you can even name them. Suppose I could write here one, and I could write here two, because classically you have a macro size of the particles. Okay, so in that case, if you are taking the example of red balls, so even they are identical balls, but you can name them. Okay, so this is according to Maxwell-Boltzmann statistics. And if suppose you are shaking that box, and at for certain time these two balls are at different positions, but even you can distinguish them. Okay, this is the second one and this is the first one. But in case of when you are dealing with electrons, so you can't distinguish even which electron it is. It is one electron or it is two electron. But they have taken this over assumption also that these electrons are obeying Maxwell-Boltzmann statistics. But it should not be like this, because electrons are quantum particles and you can't name them even. It is the first electron or it is the second electron. So how they can obey this Maxwell-Boltzmann statistics? Because according to Maxwell-Boltzmann statistics, identical particles are, if you have identical particle, you can distinguish them. But according to of when you are considering the electron. So this is why quantum field electron theory has been developed, because there are some drawbacks for the classical field theory. And here is a Sommerfield name person who proposed this theory. And because according to that, because in the Maxwell-Boltzmann statistics they are saying electrons are distinguishable particle, but this could not be like this, because because electrons are quantum particles and they could not obey classical laws. It should obey quantum laws, and they can't obey even this Maxwell-Boltzmann statistics. So this is how the quantum field theory developed. So, and now the postulates of quantum mechanics. What are the postulates of quantum mechanics? Because what are quantum laws? Because in case of classical mechanics, we say that electrons are obeying classical mechanics, and according to classical mechanics, electron can take any energy. Okay, that means it has continuous energy spectrum for the particles in classical mechanics. But in case of quantum mechanics, we know that using that Bohr model, you know that what is Bohr model? According to the Bohr model, we know that this nucleus is present at the center, and electrons are moving around this nucleus in a circular orbits. It is not like that they can move anywhere. They can move only in the circular orbits, and they have definite energy. But in case of classical mechanics, electron can take any energy. Okay, so it should not be like this. It's according to quantum, this energy of electron is quantized. It is fixed, and it has discrete values. Okay, so but that was not in the case of classical mechanics, because in case of classical mechanics they are saying they have any energy. Okay, they can have continuous energy. But what quantum says, according to quantum mechanics, energy of electron is quantized. It can't take this continuous energy. It has discrete value of the energies, and electron can move only within these energy levels. Okay, so you can see here this figure, this is shown in this picture. And you can see here electrons are in circular orbits. You know, first orbit is 1s2, 2s2, 2p6, and 3s2. So like this, these electrons are in the fixed energy levels, and that means they have discrete energy. That energy is quantized. And even this quantum mechanics, according to this quantum mechanics, those electrons obey Pauli exclusion principle. What is Pauli exclusion principle? That no two electrons can have same energy or same quantum number. And if they don't have same energy, so they can have no two electron on the same energy level, or no two electron can have same quantum number that are identical. So these are some postulates for the quantum theory. And in this quantum theory, you can see that these electrons do not obey Maxwell-Boltzmann statistics, and in this distribution says that electrons should follow Fermi-Dirac statistics. And according to this Fermi-Dirac statistics, if you have identical particles but they are indistinguishable particle, you can't distinguish them. And in this theory, they have also made an assumption that electron in metal experience constant potential. But in case of classical theory, they said they are under zero potential. But here in the quantum mechanics, they are saying electrons are experiencing constant potential. And even in this theory, they are also ignoring the interaction between electrons. Okay, but in case of classical, they have also ignored this interaction. But in case of quantum mechanics, they are also ignoring this interaction between the electron. And this is a quantum theory of free electron. Okay, so and Sommerfield proposed this theory. According to him, energy of electron is quantized, and they obey Pauli exclusion principle. They follow the Fermi-Dirac statistics, and electron in the metals, they experience constant potential, and even interaction between electron is ignored. So is it clear, students? So here we are just we are doing just basic part of this quantum theory and classical theory of free electron. So now the merits of the quantum theory, it explains the phenomena that have not explained in the classical field theory. So these are some points that heat capacity or specific heat of matter was not explained in the classical field theory. The expressions they are getting, they are not matching with the experimental values. So using this quantum theory of free electron, they explains these phenomena which those were not explained by the classical theory of free electrons. But still there are some demerits because it cannot explain the metallic properties. Those are exhibited by only certain crystals, because if suppose there are so many crystals and only certain crystals obey or they have metallic properties, means some are metals. So if they are not having metallic properties, so what the other crystals are, means they even don't explain the difference between semiconductors, insulators and metals, and they even do not explain why the certain metallic crystals have definite structure, because in the first chapter we have seen that there are different crystal structure, FCC, HCP, but they can't explain why some crystals have some definite structures only, why they have HCP, why they have FCC. So even this quantum theory of free electron that was proposed by Sommerfield, it is unable to explain these phenomena. Okay, so is it clear, students? So here we were discussing about the merits and demerits of quantum theory and classical theory. Even they has been explained in the 1900. Okay, classical theory we are discussing here. It was proposed in 1900, and this Sommerfield has proposed this theory of quantum in 1928. Okay, so now we are in 2021. We are here. So in between these time, we have so many research over this and so many assumptions they have made earlier. So they have refined. So that the properties we didn't have been explained by these theories, they have been explained after certain that point time. So now I will share you my next PPT. Is it clear? So earlier we have only discussed the classical theory of free electron and quantum theory of free electron. we have just discussed the postulates they have made at that time, and what merits they get because they have explained some phenomena, and what they do not explain, what the properties they have not explained. So why they have not explained? Because this is a failure of that free electron theory, even the classical or even the quantum theory by the Sommerfield. So because of the oversimplified assumptions that they have made, because in that case they are saying electrons are moving in zero or constant potential, but we know that electron in a metal or electron in a metal or crystal, they have some potential because they experiencing potential which is complicated, and we can take reasonable approximation for that, but we can't ignore that potential. And in those theories they have totally ignored the potential, and they're saying okay, it is zero or constant potential. But this is not the case because potential experienced by the electrons is still complicated, and we should take this in account. If you take these interactions between the electrons and the potentials, you will consider, obviously you will get the different results.